Okay, let's go on to question 4. So how would Al-Khwarizmi have solved this? Well, the first thing, he would have doubled the equation. So we get x squared plus 10x equals 56. And so he would have thought of x squared as that square there, x by x. And the 10x, we extend the x by 10. And so there's x plus 10 times x, so that's x squared plus 10x is this area here, is equal to 56. So we know how to do this. We sort of cut this in half here, and we take that strip down there, and then that creates a little square here, which is a 5 by 5 squared. And so we would have gotten x plus 5 squared equals 56 plus 25. So x plus 5 squared equals 81, so x plus 5 equals 9, so x equals 4. Okay, in question number 5, we want to prove the law of the lever for incommensurable. Given that we have the law of the lever for commensurables, and we want to use the Eudoxan definition of incommensurability. So the law of the lever for commensurables says that if A is to B, so that's the weight A is to B is M is to N, then the distance from the fulcrum to B to the distance from the fulcrum to A is M into N. Okay, so we want to show that it's true for incommensurables. So we're going to do a proof by contradiction. So, we are saying that there exists A and B such that A is to B is not as f of B is to FA. So remember, A and B are weights, FB and FA are distances. Okay, by the definition of proportionality, that means there exists integers m and n such that A is to B is m to n, and FB to FA is actually not equal to m to n. So this is just contradicting the Eudoxan definition of contradiction. A is to B is greater than m is to n, but FB to FA is not greater than m to n. A is to B is less than m to n, and F to B to FA is not less than m to n. So this is just contradicting Eudoxan definition of proportionality. Okay, so case 1 is not relevant since that's the commensurable case. So, so we can assume then that we can get rid of 1, and we're just interested in cases 2 or 3. So let's say we've got 2 holding such that A is to B is greater than M is to N. And well, if FB to FA is not greater than M is to N, then either it's equal to M is to N or it's less than M is to N. But again, it can't be the first case because that's the commensurable case. So we must have that A is to B is greater than M is to N, and FB to FA is less than M is to N. Okay, so what happens now? So that means, so if A is to B is greater than M is to N, that means then N over M times A is greater than B, but N times FB is less than FM times FA. Since the distance from the fulcrum to the weight N over M times A, remember that's a commensurable case, is M over N times the distance from the fulcrum to A. We have N times that distance from the fulcrum for N over M times A equals M times the distance from F to A. So N times FB is less than N times F N over M times A. So the distance from F to B is less than the distance from F to N over M times A. But that's a contradiction, since N over M times A weighs more than B, but F of B is closer than what the distance from the fulcrum to that N over M A is. And the other case for 3 has, you get a similar contradiction. Okay, so that shows that. Okay, and the final question is to do with the paraboloid, the parabola under rotation. So since it's a parabola, we have that there's some parameter times the abscissa is equal to the ordinate square. So if we look at our situation here, so for example, we've got this AS right here, that looks like a abscissa, and that has ordinate OS. Okay, so K times AS equals OS squared. And then the one we've got, if we look at right going to the height, this is the height of the paraboloid, and this is the base. That's also on the parabola. So we've got K times AD equals BD squared. So that means we can solve for K. We can find out what the parameter is. It's going to be BD squared divided by AD. So in general, what we're going to have is BD squared on AD times AS. That's just generic abscissa equals OS squared. Okay, so the circle of the paraboloid on the lever, so right here, weighs, so remember we're putting it all at this point AH over here, that is going to be AH times the area of this circle. So we can think of that as the whatever thing it's exerting on the lever. So that's AH times pi BD squared on AD times AS, because on the parabola. So we know AD equals AH, so that circle is pi times BD squared times AS. Okay, the AD and the AH is going to cancel out. The circle of cylinder on lever weighs AS times pi ms squared, right here. But ms is the same as bd, so it's pi bd squared as, and so we see those two circles exert the same thing on the lever. So the collection of circles we have at the paraboloid at H, so we think of the paraboloid as just dangling from H. It's balanced by the cylinder on AD. And that's the same thing as if the whole cylinder was at the halfway point. So that means that shows us that the paraboloid is half the volume of the cylinder. And since a cone is 1/3 of the cylinder, the parabola is 1/2 divided by 1/3 is 3/2 of the cone. And that finishes off our homework.